Good morning. My name is Steve Maher. I'm with Risk Management Professionals, and welcome to our webinar series. This is actually module for those of you who are following along to our HAZOP and LOPA facilitation series. This is module 12, and we're going to kind of couple that with an overview of the 2014 CCPS guidebook on enabling conditions and conditional modifiers. What are we doing this for? Risk Management Professionals is an engineering consultancy specializing in process safety. A lot of you know us for our HAZOP and LOPA facilitation support, or for some of the folks who don't have an entrenched program at their facility, we provide wide range PSM, RMP, and state program support such as CalARP. These are the things we do as part of our engineering services. Now, to do our job properly, we have an ongoing technical outreach program so that we can go ahead and emulate our best practices for the things that we do to our own staff. And also we found a long time ago that a lot of people would benefit from that, so we go ahead and turn on the camera and create webinars for various modules that we feel might be helpful to help provide best practices for techniques associated with process safety. This webinar is being used as using a GoToWebinar medium. What that means is when you started up your computer on your screen, you probably saw a larger window with the presentation, the PowerPoint presentation, and a smaller window with the video of the speaker. Those windows are movable. You can grab the speaker image and move it to other locations on your screen. You can also resize the windows if you want to. If you do have any technical problems, please feel free to use your chat interface. And actually, it's called something different. It's not chat. What is it, Alex? Okay, it's your questions interface. There was some confusion about that at one point. Go ahead and use that, and you'll be able to broadcast a question directly to our producers, Alex Metulev and also Morgan McVeigh. This can help you resolve technical issues, and later on during our question and answer period, you'll be able to go ahead and post a question. If you do need some technical support too and your computer's not working well, call 877-532-0806. That's 877-532-0806. That's on the bottom right-hand corner of your screen, and somebody will do their best to help you out there. Okay, so that's what we're doing today. What we're going to be focusing on is an overview of the 2014 CCPS guidelines for enabling conditions and conditional modifiers as part of your LOPA implementation. So what we'll be doing is providing a little bit of background and then get into the meat of it shortly. The key presenters are going to be myself, Steve Maher, and also John Johnson. A little bit of background. A lot of you have seen me or know me. I've been in the business for quite a while, been around the block a few times, and I've had the privilege with working with some phenomenal people at the Center for Chemical Process Safety in the mid-1980s as part of the technical steering committee as things were ramping up to address the tragedy at Bhopal. I've also had the privilege of working with some very good professionals over the years and been involved in some very interesting projects, including a landmark study that was done with a platform safety shutdown system effectiveness study in 1990 associated with offshore platforms, of course. And that was actually during the time when these instrumented systems, well, actually, a lot of the analog systems were morphing into instrumented systems. So back then, a lot of the techniques that you now see patterned as part of your hazard analysis approach were used at that point to make some fundamental decisions on what types of architecture you might want as part of your instrumented systems. John Johnson, also a key member of our staff. He's got chemical engineering degrees, bachelor's and master's, a smattering of HAZOP and LOPA experience in a variety of industries, including upstream oil and gas, downstream ammonia and chlorine. Also has been involved in quantitative risk assessment studies and provided a variety of support activities for CalARP, PSM, and RMP. So the key topics we're going to talk about today, I'm going to start with a little bit of an alignment so that we'll provide some background to kind of set it up so that John can provide some details on the specifics of application of enabling conditions and conditional modifiers. After he's done that, there's also a change in the regulatory landscape with respect to the requirement for implementation of LOPA. I want to talk about that a little bit so that you can broaden your horizons a little bit, although LOPA has been a terrific tool for decision making and helping with technical risk assessments. The reality is there's some other things on the regulatory horizon that make its application all the more important. And I wanted to talk a little bit about that later. So let's talk initially about what's out there. This slide to me provides a really good perspective on the importance of the work that we as safety professionals do. There have been some horrible tragedies over the years, and as we drill deeper, we run our process units hotter and at higher temperatures, these tragedies are always out there, and it's important that we understand those and can properly deal with it and implement management systems. When you look at all these tragedies, there's a fundamental core of management system failures that have resulted in failure of the safety mechanism, or basically setting it up so that you're running outside your safety margin to actually cause the accidents. When you look at the core issues, the root causes, they're usually relatively simple precursors in initiating events, and it's usually a failure to maintain the design intent. So long ago, rather than address each issue individually or blame the operator for an accident at the plant site, the idea was to look at the management system. What in the management system has not worked properly, and it's always something associated with that management system that hasn't functioned. And so developing safety management systems to address that has been the fundamental issue to help you understand and control accidents at plant sites. Now, what's the core part of that? To control the hazard, you need to understand the hazard. So process hazard analysis is fundamental for achieving the objectives of implementing a safety management system. When you look at the spectrum of tools, many of you are familiar with the simple tools such as checklist, what-if studies, hazards, and some of the more complex tools such as bow ties, fault tree analysis, event tree analysis, and all the elements of quantitative risk assessment. LOPA is on that end where you can apply quantitative techniques to help make decisions on system architecture and identify if your risk thresholds are being met. And HAZOP, right there in the center in green, is your workhorse for helping identifying scenarios that lead you to understand the hazard and help you make decisions. In the next segment, what I'd like to do is talk a little bit about the importance of LOPA and why the tool it exists and what do you do with it. The reason why there's most of the focus currently with LOPA has been on refineries, and we'll talk more about that later. There's a photograph of an offshore platform here because a lot of the issues associated with offshore platforms, what makes them unique in terms of difficulty in egress, the importance of the difficulty in emergency response, and the importance of protecting personnel made the importance of system reliability for protection systems all the more important. And for that reason, a lot of these techniques evolved early in the game for offshore platform protection. What I want to do is help us understand the big picture here, just real briefly. A risk framework is fundamental in understanding the importance of the hazard and supporting decision making. Just knowing something that's a very high consequence doesn't really tell you its importance or what protection features you need. Perhaps it's something that's almost impossible to have occur. Also, conversely, if something is very high frequency or happens very often, that also doesn't necessarily mean that's something you need to protect for. Perhaps it's just an operational upset that really causes no damage to equipment or harm to personnel. So really getting that big picture framework of understanding the ultimate consequences, the severity of those, and also the frequency of getting there, and breaking that down into the scenarios of how that consequence can occur are really fundamental to our understanding of risk and making decisions. And that's what I want to, that's the fundamental framework for all the different hazard analysis tools and what we're doing for LOPA. When you look at the evolution of systems, when we went from analog systems to instrumented systems, the advances in electronics facilitated the application of more reliable control and protection equipment. But of course, with that reliability, it enabled us to operate our units hotter, higher pressures, drill deeper, and push the margin of safety all the more, which meant that you want to even improve the reliability of your protection features even further. So as this evolution occurred over the past few decades, going from analog equipment to smart sensors, to voting logic, to lower reliability instrumented systems, to very high reliability instrumented systems, For those of you who are the practitioners of this, you'll recognize SIL 1, SIL 2, and SIL 3 definitions in the lower part of your screen as a reflection of system reliability. In tandem with that, you have procedures and industry guidelines such as 61511 that provide a framework for designing this equipment and also maintaining it to achieve that high reliability. So it all feeds upon itself. As we evolved with instrumented systems, we needed to look carefully at reliability, and for that reason, the layer of protection analysis technique and other quantitative techniques became even more important. So what we've got today is a wide spectrum of equipment out there, from simple analog devices to high-level instrumented systems and voting logic. And so the tools that we apply need to balance all those issues. We not only need to understand the hazard, but we need to go ahead and properly evaluate all these different systems that can provide protection so that we can make good decisions, properly apply our resources to make sure that we achieve the optimal level of safety that we need. So this leads us to the importance of LOPA as a tool to evaluate the effectiveness of the protection features that you've got out there. So in the next segment, what I'd like to do is talk a little bit about some of the key elements of LOPA and set it up so that we understand how enabling conditions and conditional modifiers feed into that, and then John's going to get into some of the details. So why LOPA? Well, as I mentioned, there's a lot of evolution of instrumented systems that require a need for quantitative techniques. Some of my early career was in quantitative risk assessment, and whereas I enjoyed it a lot, the depth of statistics, the absolute number crunching, and all the other things that went with a QRA were kind of, it was kind of an obstacle to communicate those issues to a lot of the people who are out there designing or operating equipment. So basically, LOPA evolved as a bridge between a detailed QRA and a HAZOP. How do you achieve the benefits of applying a quantitative technique in a way that's digestible and can easily get you the answers that you need to make fundamental decisions? It's interesting to note that the original LOPA guidebook was subtitled Simplified Process Risk Assessment for that very reason. You have to make decisions, you need the quantitative information, but the magnitude of effort for a full quantitative risk assessment was sometimes something that could not be achieved. So LOPA uses relatively standard initiating cause frequencies and independent protection layer, or IPL, probability failure and demands. Sorry about the terminology, but basically a reflection of the equipment reliability to keep the analysis simple, to make it something so that you can take a good high-level look at things and make fundamental decisions on a quantitative level and get useful results from what you're doing. Kind of to help us pull all this stuff together, it's important to realize that all the hazard analysis techniques are scenario-based assessments. This one slide, I think, says a lot with respect to how these things integrate. When you're looking at this is a simple gas blow-by case that is used where we're looking at a simple fault tree representation. The fault tree, as some of you recognize the AND and OR gates, and your undesired event at the top, and the fact that you've got an initiating event that has to happen in conjunction with the failure of safeguards to really get to that undesired event. Well, when you think about it in HAZOP space, the causal event is basically, in this case, a level control valve failing open. You've got consequences clearly identified, and you've got safeguards, also part of the fault tree. Well, in the same way, the LOPA, using different terminology, is really doing the same thing to really clarify what the scenario is and what you can get out of that. For LOPA, you're looking at an initiating event that in a HAZOP is characterized as a cause. The LOPA, you're also looking at the ultimate consequences, and we'll talk about that more on the next slide. And also, LOPA uses the concept of an independent protection layer. It's really a safeguard with an emphasis on its independence and reliability. So all these things come together. Regardless of what technique you're using, understanding the scenario is very important, and we'll get more into that in a few minutes. So LOPA is actually quite easy. It's meant to be easy. It's meant to be a simplified process risk assessment. So the development of the scenarios has to be straightforward. You basically got in this slide an initiating cause and the things that may temper the likelihood of that initiating cause to have an effect. Basically, the primary loss event only occurs after the failure of safeguards. So to get to that primary loss event, your initiating event has to occur, and you're basically multiplying it by the probability of your enabling conditions, such as external temperatures that can temper whether or not you can actually reach the primary loss if safeguards fail. If you get to that primary loss event, it doesn't necessarily mean that you have your ultimate consequence of equipment failure or personnel injury. It depends on conditional modifiers. Things like operator presence. If you have an accident and nobody's there to get hurt, well, your consequences associated with personal injury are zero. So the conditional modifier is a way to blend in the probability and multiply it with the primary loss event frequency to get an understanding of how likely it is or what's the frequency of getting to that ultimate consequence. So, and different people approach LOPA differently. Some people stop at the primary loss event, they bin these things, and they look at all the scenarios that lead up to that. Most people take LOPA over to its ultimate consequence: equipment failure, environmental damage, or personnel injury, or even a fatality, and pull together the conditional modifiers that buffer the primary loss event. A symbol that many of you may not be familiar with is the pi symbol in the boxes in the center there. The capital pi is just basically a multiplier. Basically, what you're doing is you're taking the product of all these things to make the LOPA calculation simple. Now, something to understand here, we're looking at one scenario. We're looking at one scenario in blue. In the yellow box, I want to make an emphasis point here. Basically, the probability values of enabling conditions and the conditional modifiers, they can vary for each cause-consequence combination, and you have to look at all these different cause-consequence combinations if you're looking at doing a complete LOPA. You may have different initiating events that lead to the same consequence, and your initiating event, depending on the success or failure of various safety features, may lead to different consequences. So all these things have to be considered after you use a tool like a HAZOP to identify a scenario, and then you're pulling it apart and getting some more quantitative information to help you make decisions using a layer protection analysis. And the enabling conditions come in as a probability, to come in as a product of your initiating event frequency, and your safeguards failure, which is usually represented as a probability of failure and demand, to get to your primary loss event, which then gets multiplied through with conditional modifiers on how likely it is to get from your primary loss event to your ultimate consequence. Okay, so now that we understand how the enabling conditions and conditional modifiers get addressed in LOPA, let's take a quick look at the mathematics. For those of you who like equations, I wanted to make sure that the slide comes in. And we're going to talk a little bit later about the importance of understanding the scenario when you're doing these kind of things. The first equation in blue is basically the concept of risk. The idea that you need to understand the likelihood of the event and the severity of the event to really get an appreciation of importance of not only the event itself, but also the importance of the safety features in their functionality to protect people, the environment, or equipment. The second and third bullets are different ways that LOPA is used. Some people use a LOPA ratio. Basically, it's a ratio between your target frequency that you're trying to achieve and the frequency of the event that you've got. Target frequencies may be looking at the likelihood of a certain consequence that you don't want to have happen. So, and the second equation gives you an idea of how this works mathematically, multiplying the initiating event frequency times the product of all the enabling conditions times the product of the probability of failure and demand of the safeguards times the product of the probability of your conditional modifiers. All these things come together when you want to make decisions. And so let's go ahead and talk about those decisions. Basically, again, LOPA is a decision-making tool. It uses a simplified quantitative process to determine if you've met your risk targets, how adequate are your basic process control systems and safety instrumented systems or high integrity protection systems in protecting the system. Are they adequate, reliable, or do you need some additional reliability there, or maybe additional equipment? You can also use it to do benefit cost ratios, also identify if you can simplify the system. A lot of people, we do a lot of capital projects and implement HAZOP and LOPA when clients are developing a design. And the interesting thing is, I see this more and more as the years go by, People are more comfortable with safety instrumented systems, and you see a lot more implementation, even in areas that aren't even proved to be a significant hazard. People are comfortable with it. Management feels happy that you've got some extra protection there. So there can be sometimes an over-application of a safety instrumented system. Well, when you're working with an engineering contractor during the design phase, that sounds all well and good. But then you're turning it over to somebody to operate at some point. Somebody's got to maintain that equipment. Somebody's got to test it. Somebody's got to make sure that it provides the functionality that's been designed into its reliability. And the fact is that if it's over-designed, that means a lot of extra resources devoted to maintenance and testing that maybe should be focused somewhere else. What's this business all about? It's all about aligning your resources to get the maximum safety benefit. When you're implementing this stuff, we do a lot of initial LOPA implementation during the HAZOP study, either reinforce the safety integrity levels that are assigned to equipment, or basically provide a baseline for it. LOPA can also provide an ability to a framework for additional details. If you've done an initial LOPA, maybe as part of your HAZOP study, and you're getting a fairly high risk, well, you can take that understanding of the scenario right from there, and then put additional probability, more accurate probability values, additional insights, study it a little bit more to sharpen the pencil and really understand what the risk is. You can also improve human error probability calculations. You can do more accurate consequence modeling, all the things to help you understand the scenarios better. So this whole idea of the hazard analysis, the HAZOP study to understand the scenario, the LOPA to quantify it, all leads you to helping you make decisions. We found that LOPA is best implemented using a team approach, either right after the HAZOP study or as part of it. And what we found is that if you implement it in tandem with the HAZOP study, it's really works out very efficiently. Again, you've already got the team warmed up with an understanding of the scenario, so why not absorb that understanding into something that can provide more effective use later on for equipment design. So at this point, I'd like to turn it over to John to provide additional details on the application of enabling conditions and conditional modifiers and a lot of the tips associated with this. So, John, it's all yours.
Thank you, Steve. I want to make sure my volume is coming through. Alex, am I coming through all right? Okay. So Steve mentioned what I'm looking at today is discussion and an overview of enabling conditions and conditional modifiers. And this is coming out of a document published in 2014 by CCPS. The actual title is Guidelines for Enabling Conditions and Conditional Modifiers and Layer Protection Analysis. I do encourage anyone watching this, if you really want to get further in depth, you want a little more information, please refer to the source material. As always, we are limited on time, and so there is only so much information I can convey. However, there are a lot of good examples that can be provided in the source material. How I broke this down is basically two sections. I'm going to talk about enabling conditions and conditional modifiers. I'll also go further into definitions in their appropriate sections. What I want to point out here is just the fundamental difference between the two. Enabling conditions are those items that's going to allow the scenario to actually occur in the first place. However, conditional modifiers assume the scenario has occurred, and now you're looking at, well, exactly what sort of hazard are we looking at and what sort of effects are we looking at occurring. So moving on to guidance on when to use enabling conditions. As I said, a little more in depth on the definition. So enabling conditions, we also refer to these as enabling event. This is a process condition or operation that's going to provide a pathway in order for the loss event to occur. We generally express this as a probability, and this of course is based on the fact that in LOPA, an event frequency is given as some percentage of time that this is going to happen per year. The enabling condition is tempering that frequency, so essentially you're going to multiply the event frequency by the enabling condition, and that's going to give you the times per year that the potential for loss event exists. But I want to point out here that these enabling conditions are neither a failure nor a protection layer. There are three typical types of enabling conditions we look at: time at risk, campaign, and then of course we have the catch-all other that is based on team discretion. One caution I want to point out, and I will once again go into this a little more in subsequent slides, the condition should not in itself be considered the initiating event if you're going to use it as an enabling condition. And once again, I'm kind of leaving that open. I will cover that more in depth later. This once again an overview of time at risk enabling conditions. There are two types. And basically the takeaway here is there are certain conditions that must be met in order to proceed to a loss event. And these conditions only present themselves for a fraction of the time. So that means we're looking at seasonal risks as well as process state risks. Getting into seasonal risks, ambient temperature. So here you can have low temperature, possibly causing freezing lines. You can have high ambient temperature that maybe could affect your cooling, as well as low humidity. Generally, for most facilities, these events are only going to occur at certain times of the year, perhaps 3 months for summer, 3 months for winter, although that's going to deviate based on the location of the facility. What I want to point out here is that these seasonal risks, they must be independent if you're going to be using these enabling conditions. So I want to point out, beware of common mode failures. For instance, if you're looking at low ambient temperature causing freezing, if at the same time it's also causing freezing in your instrumentation, you don't really want to take some sort of enabling condition probability that's going to temper your overall likelihood of the event occurring. Going back to what I said earlier about not overlapping and doubling up, the seasonal condition cannot be the initiating event. It is used as an enabling condition. I bring this up because in my HAZOPs a lot, I'll use low ambient temperature as an actual cause. So if you're going to use that as your cause, obviously you're assuming it's happening 100% of the time. You can't then subsequently go to your LOPA, use enabling condition saying, oh, well, it's only happening 50% of the time. It's a cause. It has to be generated as 100% of the time. Process state risks. So this is, unlike seasonal events, this is an event that occurs when the process is in part of a non-continuous operation that might be conducive to the scenario occurring. So this could be loss of cooling during reaction. Obviously, if you have an exothermic reaction, you want to make sure that your system is being cooled to keep your reactor within the design temperature. Of course, out of reaction mode, any other time, it's probably not an issue, and so you only want to look at it for those times that there might be some sort of loss event that can occur. Another quick example is reverse flow. So if you have an isolation valve that fails to close, leaving the potential for reverse flow from a particular vessel, however, during the majority of your operations, the upstream pressure isn't actually going to allow that reverse flow to occur. What you want to look at is those times the downstream pressure might be strong enough to actually provide this reverse flow that's going to lead to your loss event. Once again, you're going to temper that event frequency with the probability of the enabling event occurring. Campaign enabling conditions, there's actually a number of different ways to look at these. These are non-uniform risks in the process due to changes in the operating conditions. So this can be a difference from batch to batch due to changes in raw materials, differences in process configuration. I don't see this a lot in upstream facilities or even in refineries. Where I see this a lot is in chemical blending plants, where I've had some that'll have 60 different tanks with 60 different chemicals. Some are related, some are not. They're changing the configuration of their pumps and how they're getting things moving to different reactors. This is where you really want to look at the enabling condition of how often and what points of time which chemicals are being used in blending. Also as a campaign enabling condition, equipment failing during particular process state or configuration. If a control loop fails during recycle, and this could potentially result in a loss event, however, the same control loop failure during feed forward or during normal operations does not cause a loss event, well, you want to temper that event frequency with that enabling condition probability. In operationally part of the year, I see this a lot in agriculture plants, especially up in the San Joaquin Valley, where they are only really concerned about summer months and they need to regulate temperature in that time. So you only really want to look at tempering your initiating event frequency for that specific summer period. And the reason is because these event frequencies, once again, are on a per year basis. So if you're looking at a pump that fails, but it's only going to happen within that time frame, you definitely want to account for the fact that is not in continuous operation for an entire year. And finally, a process involving a family of reactive chemistry or other composition-related, process-related variables. This considers that it's related to the very first bullet. It considers that at certain times, raw materials used in a process may be more hazardous than at another time. Other possible enabling conditions, as always, there's a lot that we leave to the team discretion, and this is based on the expertise in the room. These are enabling conditions that are not specifically time at risk or campaign situations. I did provide an example. This came straight from the CCPS guidance. So, for instance, a certain chemical is required to be stored in a refrigerated environment. However, the chemicals are only stored 30% of the time. So you have a 0.3 probability that a loss event will occur if you were to have a failure of that refrigeration system. Once again, you could probably argue that this is seasonal. You could argue that this is campaign. Purposes of this example, we put under the other possible enabling conditions. So also key is when not to consider enabling conditions. Once again, they're kind of long-winded. These are directly from the CCPS guidance. I'm going to read a little bit of it and then explain what the takeaway is on each of these. So the first one, the LOPA analysts have insufficient knowledge of enabling conditions to employ them correctly. I think this ties in directly to the next one, which is insufficient data or information is available to assess the probability to be assigned to enabling condition. My take home from both these points, if you want to use enabling condition, if you want to temper these frequencies that are provided statistically or by the facility management, you need to have a reason. You need to have expertise in the room. You need to have people who know exactly what is going on in the field, exactly what is going on with the chemical, exactly what is going on if there is a release event. Furthermore, the company or facility's established LOPA procedure specifically indicates that enabling conditions are not to be used in LOPA for whatever reason, or a potential enabling condition does not meet company criteria. In this case, you simply leave it as a 1. You leave it as 100%. You focus more on your IPLs. You focus more on your recommendations, whatever you need to do to meet your LOPA requirements. And finally, the company or facility does not have the resources, capability, or practices in place to properly assess, document the use of enabling conditions, and maintain their ongoing validity. At the very end of this section of the presentation, I'm going to go a little bit into documentation and maintaining that validity. So I'm going to kind of save really hitting this home until then. Moving on into guidance on when to use conditional modifiers. To reiterate what I said earlier, the enabling condition is what's going to allow this loss event to even proceed in the first place. The conditional modifier, once again, is what is going to allow this to proceed to its ultimate potential consequence. Generally, this is going to be an effect on personnel, effect on the business, effect on the environment. So it's a probability of a detrimental impact. It includes a probability of, this is the list I'm going to be covering in subsequent slides. It's hazardous ignition, atmosphere, the probability of ignition or initiation, explosion, and the probability of personal presence in the area and as to whether or not they will get injury or fatality due to this particular incident. Conditional modifiers should be independent. This is both of cause and other IPLs. It is very easy, especially when you get to personal presence modifiers, to double count. And I will go into details of that a little further on. They need to be audible and they need to be managed. You need to actually control these modifiers. You're tempering these LOPA events in order to meet your LOPA requirements. So let's start off with the probability of hazardous atmosphere. Once again, all these examples, all these statements come directly from the CCPS guidebook, and I am kind of following their format on introducing them to you guys. So the release occurs but does not necessarily result in a hazard. That's common sense. So a lot of times in a HAZOP, they'll have a team, and I'll say, okay, what's the severity we're going to get here? And everyone says, oh, you'll have half the team going, well, nothing will happen. You have half the team going, well, the ultimate potential consequence is a fatality, the worst thing that could happen. Well, this is where we actually consider what's the probability of that event actually happening as opposed to a HAZOP where we just assume the worst potential consequence. So for instance, a toxic. We have a release. That's going to depend on a lot of things. It's going to depend on the atmospheric conditions, the chemical itself. What is the probability that the person is exposed to a lethal dose? That's going to depend on the dispersion, concentration, what's in the surrounding area. Also on the same vein, oxygen deficient and enriched atmospheres. I see this one come a lot, especially in units that perhaps have nitrogen purging or it's happening inside a building. So what I want to point out here is this is dependent on the hole size, the flow rate, and the size of the building. All these factors are going to contribute as to whether or not someone will perhaps have a fatality due to the asphyxiation hazard. What I also want to point out is these are somewhat complicated to analyze in scenario, which is why you really need expertise to come up with these probabilities and a deep discussion on exactly how probable it is that someone could possibly have a fatality due to this event. Caution I state here, be careful not to double count IPLs. It's one of the examples I wanted to use. So a lot of times you would bring up this modifier and, flow rate, size of building, and you say, oh, we have, say 6 air exchanges per hour. So we're not going to build up that asphyxiating atmosphere. However, a lot of times we'll probably have taken those air exchangers as an IPL. If that's the case, we do not want to consider that in our calculation of this conditional modifier. Furthermore, this is an example. So just a quick example I wanted to put in there. This is release of flammable liquid with a high flash point. The only time this is going to result in a pool fire is under extreme high heat conditions. So once again, we're only looking at perhaps summer months or when the heat is high enough where we can actually get this ignition of the flammable liquid. So what is the probability of these conditions occurring at the time of release? So there's an initiating event, control valve failure leading to overfill from a storage tank. The frequency, and this is based on, I'm ballparking it, but it's based on facility guidance, or it's based on a lot of guidance that I've read in the past. Frequency is 0.1 times per year. What is the probability of high temperature occurring? So once again, I ballpark this. What we're saying here is 3 months out of the year. It's during summer, so your probability is 0.25. That's going to temper the overall frequency of the event, giving you the frequency of hazardous atmospheres being 0.025 times per year. To go back to my point about making these things auditable, 3 months out of the year is a ballpark. Sometimes the summers are hotter, sometimes the summers are not, sometimes you only have 1 month of high extreme heat. My point I'm getting at here is you should actually have weather data to back this up. I will hammer this home a little bit further later. Probability of ignition or initiation. This is highly scenario dependent. It should be evaluated on a case-by-case basis. You really want to make sure you have expertise in the room who, as I said earlier, understand the chemical, understand the process, understand the equipment, understand the topography. All of these things can lead to whether or not you can build up an ignitable atmosphere or an explosive atmosphere, which we'll get to in a moment. So there are a couple of different ways you look at probability of ignition. First off, you look at it from probability of ignition inside process equipment. These are some of the events you look at. One of the ways I see it the most time come up in a HAZOP for inside process equipment is you lose your nitrogen purge, or for some reason you get oxygen ingress into some sort of tank that has a fuel source or a flammable material. So you've got your fuel, you've got your oxidizer, so now you need to think about your source of ignition. This is where your probability comes in. What are the potential sources of ignition that may be seen? Here is just a very partial list that you need to consider. The list in CCPS is about 4 times this size, and if you really were to talk in a study, I bet you could find double that. So static electricity generation during filling, agitation, etc. I won't go too deep into it. I am actually familiar with incidents occurring from static electricity generation during filling, blowing the ropes off storage tanks. This is just something I've seen. So if we were bringing it up in HAZOP, I know we definitely need to adequately look at this probability. Charge accumulation from ungrounded conductors, any rotating equipment in the process, mixers, things like that are within the vessel. Internal, external surface temperatures. Your internal surface temperature can be dependent on your external surface temperature depending on how the vessel is put together. Probability of ignition outside the process equipment. So on the same vein, you consider all the sources we just spoke about. What we also want to look at is equipment operating in the area, hot work in adjacent units, and properly designed or installed electrical equipment, cell phones, etc. One point I want to make here, which once again falls back to the expertise required, is the dispersion that happens on a release really counts heavily in the scenario for 2 reasons. It accounts for and against the scenario. If it's a very wide dispersion and you're keeping your concentration above the LEL or below the LEL, you might not necessarily build up enough atmosphere in order to have your ignition event or your explosion event. However, the wider the dispersion is, the more of a probability you have of affecting an adjacent units or finding that source of ignition that is required in order to cause this to go to a hazardous event. Other factors to consider, well, I kind of just went into this. Dispersion area of the flammable material. Does it extend beyond the unit sufficient to find other ignition sources? The release duration, the minimum ignition energy required, and the probability of an immediate versus a delayed ignition. Similarly, looking at probability of explosion, as I mentioned earlier, conditions may allow for the possibility of explosion. However, it's not always 100% certain that the explosion will occur. There are several different types of explosion probabilities you want to look at in your studies. One is a probability of a dust explosion, the probability of vessel rupture explosion, and the probability of a VCE or a vapor cloud explosion. Start off with the probability of dust explosion. Dust explosions are interesting in the fact that they require actually 5 simultaneous factors to occur in the first place. So if you have a release of flammable dust, it needs to be confined, needs to have sufficient accumulation, and I put a reference here to NFPA 654 because that does adequately define what that accumulation level is. It needs to be dispersed. You need to have a sufficiently energetic ignition source and a sufficient concentration of an oxidizer. So your probability you want to look at here, if you're in a team, well, you just need to make sure what the probability of all of these 5 happening simultaneously. So maybe there's, based on the topography, you have a high probability of confinement. However, based on the volume, you don't have a high probability of sufficient dust accumulation. You take all of these factors into consideration when you're tempering your event frequency. Probability of vessel rupture explosion. Here, so vessel rupture explosion, once again in HAZOP, we're looking at the ultimate potential consequence. So what we'll say, I'm like, okay, this goes, and the worst possible thing that happened. The team will always say, yes, the ultimate potential consequence is if this ruptures, we have an explosion, and there's fatalities, maybe multiple fatalities. However, a lot of units also say, well, you know, this is dependent on the expected pressure. And there are 2 approaches here. Once again, we can do the HAZOP method, assume catastrophic failure. It's the most conservative. It's obviously the easiest. It's useful if you don't have vessel design documentation. If there is not supporting documentation to say, you know what, we will not exceed the design limits, probability equals 1, you move on. The other one, which is a little more true to life, is assume a hierarchy of failure. This is a probability that is based on the percent that the MAWP is exceeded. So once again, if you have a slow buildup of pressure, maybe only a percent or 2 above your pressure limits of the vessel, you might have a chance of maybe releasing from a flange, maybe from a coupling, some weak point in the system, or maybe based on hydro testing, there's no possibility at all. You want to consider these in your probabilities. I do have an example on the next slide. For this example, I formed out a little bit more how you would see tables in use in a LOPA. It's not exactly like a PHA Pro layout, but it gives the nuts and bolts. So your initiating event. This is from CCPS guidebook. Pressure letdown valve fails open. It allows high pressure fluid in the vessel. Given frequency is 0.1 times per year. Not using any enabling conditions here, so probability of 1. The conditional modifier is a probability that the source pressure of the upstream high pressure fluid is sufficient to result in high enough pressure in the vessel to exceed ultimate strength of the storage vessel when the initiating event occurs. So basically what this is saying is got together, they looked at the percentage that it's over the limit, and they calculated a value of 0.1. Applying that as well to our IPL, in this case a pressure safety valve, with a probability of failure demand of 0.01, we get our scenario frequency, which is 0.0001 times per year. So still moving on into other methods of exploding things. Vapor cloud explosion, kind of one of the ones that is, you know, we talk about this a lot in HAZOP. We drive it home because it can sneak up on you and it's highly hazardous. But a vapor cloud explosion, it assumes some degree of confinement. So you're dispersing whatever your flame material is, it's releasing. Is it going to disperse far and wide? Are you going to be below your LEL? However, what if you have, as I said earlier, a certain topography, you have other units? What if you're enclosed in a building? Whatever reason, if you have some degree of confinement, there's going to be a higher potential for this explosive atmosphere to develop. However, if you're on an open plain with nothing in the area, it may be a less probability. This is where the team expertise comes in. If you can figure out the probability that you will actually have this vapor cloud explosion, you can temper the initiating event frequency, and perhaps that'll help you to meet your LOPA requirements. This probability may also be based on a fraction of time that the vapor will be in the confined space prior to ignition. And this goes to the cautious considerations, as I said earlier, local terrain. You also want to look at your wind direction. Where's the wind blowing it? Perhaps the wind blows it into an area and disperses it so there's no issue. On the other hand, perhaps at that time of year, perhaps the data shows that the wind is going to blow it within a structure or somewhere we can build up that vapor explosive atmosphere. Probability of personal presence. This modifier is probably the one I see and use the most, and it's one that needs to be approached with the most caution. So in a nutshell, probability that personnel be within the area of effect during a hazardous event. This is evaluated as a fraction of time. Typically, a question we'll ask in a study is, okay, how many operator rounds do you have? Is it less than 2 hours per day? Less than 10% of the time, 24-hour shift period. What you also want to make sure you're considering is all the personnel that might be in the area. So As I said earlier, this is highly dependent on the area of effect. Depends on how big that release is going to be. If it is purely local to a unit and you really don't have maintenance personnel, operations personnel, housekeeping, anyone in the area, then yeah, you definitely want to take this modifier because the effects will not be as bad as they feasibly could be. However, this personal presence modifier needs to account for all those personnel, all the personnel I just mentioned. Maintenance, personal performing transient operations, and once again, dependent on the area of effect, if it's a big enough release, you want to look at administration, especially if you have a control room where you have it manned 24/7, and that is within that area of dispersion. Personal and adjacent units, startup and turnaround, typically you're going to have different personnel needs and should be valued separately. Generally in a HAZOP and LOPA, we do startup and turnaround as their own separate nodes anyway, since they are unique to normal operation. This should not be considered if personal presence is required for initiation, i.e., so an operator is actually going to turn the valve, and that is going to cause a release event. They're already out, so we already know the personal presence is 100% of the time. Or if, based on training, based on procedures, if an alarm sounds, personnel are going to go out to investigate the alarm, once again, 100% of the time if they're following the rules of the facility. And it should also not be credited if considered in severity development. Just for example, on that one, a lot of times if you're looking at severities, this is laid out by the facility. So perhaps facility gives 4 for a single fatality. However, they give a 5 for 3 to 5 or more fatalities. If you've already considered that and you're already saying, well, we gave it a 4 because there's only one person out there, you've already used your modifier. Don't double dip and give yourself an unrealistic LOPA. Here's another example on probability of personal presence. So a pump fails to operate, leading to an increased level of feed accumulator, with potential to pressurize the vessel in excess of design pressure. Once again, pump failing to operate based on the frequency table I referred to gives 0.1 times per year. No enabling condition. Conditional modifier I use here, presence of personnel. So operator, 30 minutes, 2 times per shift, and 2 shifts daily. In maintenance, 2 hours per week. Obviously, you can see I did this to make the math simple because it came out with a probability of 0.1. I took credit for a PSV as my IPL, giving a scenario frequency of 0.0001 times per year. So when not to consider conditional modifiers? Once again, directly from CCPS guidebook, if the organization's approach is used to implicitly include conditional modifier probabilities when selecting a consequence severity category, I just talked about that, then their explicit use in LOPA would be double counting these factors. If the organization judges that the uncertainties or complexities involved in incorporating conditional modifier values in LOPA are too great to warrant their use, we'll get into that later, but this does have to do for accounting or making sure certain standards and rules are in place to guarantee that this modifier can be applied. If the organization considers that the difficulties inherent in validating conditional modifier values are considered to be too great, and if the organization chooses to use a conservative approach, basically just giving everything a probability of 1. So as I was alluding to earlier, documentation and validation. So just like with an IPL, modifiers require justification. You want to reference statistics, look at your calculations, dispersion modeling. What I want to point out here, once again, your dispersion modeling, I've hit this 3 or 4 times, and I think it's because it's something I've only really thought about as I've done LOPA, that, you know what, we need to look at how big this is going to be. In HAZOP, I always just assumed it was massive and anyone in the area was going to be hurt. We really want to give a true quantitative analysis of what's going on. We really want to have a good idea how big this dispersion is going to be. How far is the toxic threshold? After that, are we looking at injuries? On the same note, weather data. You want to have supporting documentation. If your team says this is going to be, for this 1 month, we're going to be 120 degrees Fahrenheit, well, then you should have weather data to back that up, that it's not the same thing in the subsequent month or the preceding month. Calibration frequencies, maintenance records, like I said, similar for IPLs, anything that is going to justify your tempering of those event frequencies. At the end of the day, you're producing a document that is justifying the safe posture at your facility. You need to justify everything you do in order to make the team agree and say, you know what, this is true. This is a true enabling event. This is a true conditional modifier, and we feel comfortable adjusting our LOPA data based on these events. I think with that, I'm going to give it back to Steve to jump into the next section.
Okay, John, thank you. Nice job. What I'd like to do is go ahead and close with a little bit of thoughts about where things are going with respect to LOPA application. By the way, Morgan, audio coming in okay? All right, very good. We've been discussing primarily the technical basis for why you want to do layer protection analysis and the importance of it during the design process and the value that it can provide to augment your understanding of hazard scenarios. On the screen, you'll see two pictures of two unrelated events that have occurred in the earlier part of this decade that have raised the attention of regulators to rethink process safety management and risk management program applications throughout the United States, and also specifically for one state program in California. The photograph on the left you'll recognize as the tragedy in West Texas. The photograph on the right as an event that occurred at a refinery in California in 2012. What that did is stimulated a lot of activity from different agencies. You'll recognize the Chemical Safety Board, Interagency Refinery Task Force, Contra Costa County, Cal OSHA, Federal OSHA, Federal EPA, and also California Office of Emergency Services and Cal EPA. I'm not going to go into any details here. We have a number of webinars that have been tracking the progress and the evolution of the changes to the standards that are ongoing in California with respect to its CalARP program and the PSM version that will be applied to refineries in California, as well as the slower evolution of changes to PSM and RMP on the federal level. We have a number of webinars out there, and also highlighted in yellow is a page that we keep on our website where we try to keep up to date with these changes. I personally use it as one-stop shopping for when I need to see what the latest regs are, even though I'm one of the contributors towards updating the page. And all of us here at Risk Management Professionals need to be on top of this because there are a lot of changes on the horizon. This is a timeline of some of the things that have occurred recently with respect to modifications and new drafts that have come out. I'm not going to go over that other than just to note that even as recently as October, changes have been made. The short story for the endpoint is that towards the end of 2016 is when California, the California regulatory community is predicting that it will actually promulgate the updated CalARP program, which is the analog to risk management programs, and also its version of PSM as it applies to refineries. So this is something, if it applies to you because you're directly in California as a refinery, you want to keep note of and carefully track. If one of your sister facilities in your business unit is in California, you'll want to monitor what they're doing from a general duty perspective. That may be something that people look to your facility to also apply. So there's a lot of good reason to keep on top of this stuff. This slide, again, I'm not going to go into details. It illustrates the changes that are ongoing just with respect to the PSM program as it applies to refineries in California. The red, orange, and yellow are the most significant changes in order of potential impact at the facility and what's going on. Blue are the things that are relatively unimpacted. And again, much more details in other webinars that you can download off our website, or if you really do, and also you can download the regulations off our website too. So a lot of information out there. That's not basically our thrust here today. What I do want to talk about is one element of those. One of the newer areas that's going as a subset of process hazard analysis as part of the PSM regulations for refineries, and also as a separate subsection for the updated CalARP that applies to Program 4 facilities, which is what they're applying to refineries, is called safeguard protection analysis. Safeguard protection analysis is a term that was coined from a regulatory perspective to basically encapsulate assessing the effectiveness of existing and combined safeguards for each failure scenario identified in the PHA. Now, the idea is to assure the safeguards are independent of the initiating event and each other. The evolution has been to make sure that the scenarios are well understood and safeguards properly characterized so that there's a clear understanding of risk and there's a sufficient safety margin at the facility. The idea is to evaluate passive, active, or procedural safeguards And LOPA is called out as a specific method that's endorsed, but they also say, of course, that you can use an equally effective method. LOPA is going to see increased application for this reason. You need to be aware that it's going to be a requirement with those objectives of applying it to scenarios identified in the PHA. So the idea is that you need to conduct the SPA, do that as part of your PHA, or you can do it independently, but usually that doesn't make a lot of sense. Now, the reason I want to mention this is just to give you a little bit of background. The other webinars that we've done and other background information have provided a number of tips on what facilities could or should be doing right now with respect to addressing this new requirement that's on the horizon for promulgation in 2016. And there's also other nuances that may make it applied as you're doing capital projects at these facilities too. So anyhow, something to definitely keep in mind. In addition to your technical basis for doing LOPA, there's definitely going to be some regulatory impetus for this too. And I'm going to skip the next two slides for that reason. And let me go ahead and summarize. What have we been talking about? We've been talking about specifically enabling conditions and conditional modifiers and their application in LOPA. But as part of this PHA module, PHA facilitation course module, I wanted to make sure that we understood what LOPA is and what it can do, and its importance in balancing design or operational options in decision making. LOPA is a decision-making tool. Verifying risk is below the tolerance thresholds, determining the pedigree or how reliable or what the safety integrity level is of key safety functions. As LOPA is recognized as being useful for this, it's also being recognized by for application as part of regulatory requirements too that come along with this recognition. As practitioners here, risk management professionals, we've got to emphasize the importance of quality application of LOPA. As John mentioned, there's a lot of things that can be done that can shortchange your understanding of scenarios and lead you to an application that doesn't really do justice to what you want to get out of it, and it may mislead you in terms of thinking you've got a safety margin that you really don't have. It's those misapplications or not careful applications of LOPA or variations from a geographical or industry sector perspective that have led to a lot of confusion, that have kind of tainted LOPA as the really good tool that it is. And it's really a kudo to the Center for Chemical Process Safety that they put together these guidance documents to help us with implementation as a best practice. The CCPS guidance documents, I'll mention more in a second. Again, phenomenal organization that's doing a very important job to help industry out. So we'll be opening things up for questions in a few minutes. But in the meantime, I wanted to let you know of some resources that are available to you that are out there. There's a long list of resources on this sheet in fine print, as well as links to get additional information. Our HAZOP LOPA facilitation webinar series. This is something where we're trying to emulate best practices for our own folks and for folks who want to also tune in. That's available off our website to look at your heart's content, no charge. The CCPS guidebooks. There's a number of good guidebooks that have come out. Again, I had the privilege of working on the technical steering committee in the mid-'80s. The CCPS is a phenomenal organization. The guidebooks are very helpful for making sure best practices are implemented throughout industry. And I'd encourage you to stay on top of all this stuff and really take it to heart. We've also, at Risk Management Professionals, we're very actively involved in writing technical papers and getting the technology out there. We pretty much every year at the Global Congress on Process Safety, we're presenting something or exhibiting something. There's a number of these papers that can be downloaded off our website that should also be quite useful to you. And also, as I mentioned before, we have a regulatory updates page that's trying to keep pace with the changes that are going on with PSM and RMP, and specifically a lot of changes that are going on with refineries right now. So our webinar series is designed to help us stay on our game. You guys can also benefit from it, and this is a list of the upcoming webinars. We'll be overviewing the guidelines on initiating events and independent protection layers in January. Also, we're trying to keep you up to date on regulatory requirements. It's obviously a moving target, but right now we think February 11th might be a good time for another update. And then at the end of March, as I mentioned, we usually support the Global Congress on Process Safety. We'll be there this year. If you're there too, please stop by and say hi. But one of our papers is on the regulatory program development. And so we're going to do a sneak preview of that on March 31st. It also helps us prepare for the conference, of course, too. So all these are coming up. They should be valuable information for you. And so now is a great time to turn it over to questions. And I'll invite Mr. Johnson to come up and join me. And this is an opportunity. This GoToWebinar interface, if you'd like to dialogue with the group or express an opinion verbally, we can go ahead and our producer, Morgan McVeigh, can unmute you to dial you in. Or if you just post questions on the question box, she'll go ahead and read those, and John and I will attempt to address them.
Okay, so our first question is the 0.1 probability listed anywhere for presence of personnel for the example provided?
No. Like I said earlier, I did that for ease of math. So the way that number actually developed was the idea that you had personnel in the field about 2 hours per day, and then you had maintenance 2 hours per week. So basically that's 14 hours plus 2 hours is 16 hours. The personal presence modifier is a fraction of time the personnel are out there. So divide 16 by 168, it's approximately 0.1. Once again, that's a calculation, not a referenced number.
Okay, so the next one is a comment that one of the participants would like to emphasize. It should be emphasized again that enabling conditions and conditional modifiers are only valid for a particular cause, consequence scenario, and there may be other causes. Consequence scenarios for the same or very similar event with a different consequence that needed to be assessed. I
wholeheartedly agree, and within the context of the study, each scenario is given its own time and its own analysis. So you would break that out by scenario, so each cause-consequence pair.
Excellent. Good comment.
Another comment is care should be taken when using conditional modifiers. In most cases, if they cannot be effectively managed, they are not valid.
Pretty much the point of my presentation is, yes, just like an IPL, you need to be able to validate, you need to be able to document, you need to be able to prove.
Okay.
Excellent.
Next comment is process safety management and risk management program regulations in California are in the process of being modified to require safeguards used in a PHA to be addressed for adequacy. The use of enabling conditions and conditional modifiers in LOPA studies to accomplish this will most likely be scrutinized by regulators throughout the state.
Once again, it goes back to making sure you have that documentation. You need to be able to prove everything you do. I mean, especially in the worst case that an incident were to occur, you need to validate why any action was taken or any action not taken.
Okay, so for another question, how important is the accuracy of enabling conditions and conditional modifiers for the LOPA?
As I mentioned earlier, this is your safety posture. You're basing what sort of IPLs you're implementing. You're making decisions on whether or not to implement recommendations or things that need to be done. So these conditional modifiers need to be applied correctly. They need to be applied accurately and with thought to make sure that you are applying them the correct way. Once again, people's lives do depend on this.
The one thing I would do to temper that is don't let yourself get wrapped around the axle. If you're doing a combination HAZOP and LOPA study with a team, team time is really valuable. You do need to make progress. If the team is spending too much time cogitating on certain numbers or debating back and forth, you might go ahead and see if a more conservative number that everybody agrees upon will still lead you to the conclusion that you need. If you've already met your risk tolerance threshold and it's not going to affect the design, then use of a more conservative and defensible number, especially if it's going to get scrutinized by regulators, could be quite beneficial. And also, if you need additional pencil sharpening, these are things that can be done after the team efforts to go ahead and improve the values, study it further, get some more accuracy, so that you got a firm basis for your evaluation or for making decisions.
Still getting requests to be further in? Okay.
Our next question is, several companies have their own internal LOPA procedures. How does the CCPS guidance for enabling conditions and conditional modifiers compare?
Tell you the truth, the CCPS guidelines reference over and over again the facility's LOPA documentation. So to tell you the truth, they are actually relying heavily on the facility itself to have developed the documentation and the rules as to when to apply a lot of these.
Yeah. What you find is more similarity than not as you go from company to company. The basic LOPA concept and how you consider and approach enabling conditions and conditional modifiers, there's more similarities than differences. The differences do come about when a facility wants to simplify so that they can get through the analysis faster and, of course, conservatively simplify. Or go ahead and if they found certain problems that exist based on their corporate culture, where in terms of how things are managed, as was mentioned before in one of the comments, the conditional modifiers are only as good as they're managed. So if certain companies have some history of problems with that, they may also, as part of their guidance for the implementation of LOPA, go ahead and put some boundary conditions on that.
Okay, our final question. For the application of enabling conditions and conditional modifiers, what are the most common causes of error?
Well, the most common cause of error, as I mentioned earlier, is double counting. Like I said, I brought up and I emphasized that personal presence because this is what I've just seen a lot, is considering it in the severity and saying, oh, well, it's going to be a fatality or it's going to be severity of this based on these fatalities. So that's where you considered it. If you then use a conditional modifier that says, oh, personal present only 10% of the time, you're affecting that statement you already made. So double counting is a huge error. Assumptions on how often people are out there. Once again, everyone thinks about operators, and that's the number you always get tossed out first. That's where you have to hammer home. What about your maintenance guys? Here's a little anecdote I'll bring up. I have a particular oil field I work with a lot. I've got an operator there, and I will say that. I was like, hey, how often do you guys have your guys out there? He's like, oh, maybe half an hour per day. And I'm like, okay, so we might take the personal presence modifier. He's like, yeah. I'm like, okay, what about your maintenance? He's like, oh, they're always out there. I'm like, wait, they're always? He's like, yeah, I've had like 4 guys out there for 5 years. So once again, you're not going to take the modifier in that case.
This also dovetails with one of the previous comments of the importance of making sure the values for conditional modifiers and enabling conditions really apply to the specific cause and consequence scenario. When you're going through these things, it's real easy for a team, if you're working with them interactively for the LOPA, to go like, okay, operator's not there, nobody's there most of the time, let's move on. And so they can kind of get in the groove of applying this without thinking it through thoroughly. But if you're the facilitator of the LOPA, you want to make sure that they're answering the question and considering things like personnel presence consistent with the specific cause-consequence scenario. And like John said, bringing in other things that may be going on at the plant site. So it's, to me, a lot of the problems that occur with respect to implementation of LOPA or the inaccuracies or the mistakes people make are done because you're not thinking carefully about the specific cause-consequence scenario and applying a logical thought process to vet the application of that. And again, that's part of the facilitator's job, is to really challenge the team, making sure that the answers they're providing are specific to the questions being asked. Gosh, if that's it, what I'd like to do is thank everybody for tuning in today. I hope you found it valuable. Any feedback you may wish to offer is appreciated, and we'll see you on the next webinar. Thank you.